Okay, hi. This video is the second video in the series of videos for chapter 2 on the relativistic equations. I will specifically talk today about the Maxwell's equations. You know Maxwell's equations from your previous courses on electromagnetism, and I will not be going to explain the physics behind that. You just know that basically this is a differential form of the Gauss's law, Ampere's law, Faraday-Lenz law, and this one actually the gradient of B equal to 0 means or comes from the fact that we don't have magnetic charges, we actually only have magnetic dipoles. Now what interests us here is something that you also know before, but actually the two equations, the two Maxwell's equations, 1 and 2 here, are actually related, or we can deduce out of them something called the continuity equation, which is the equation of continuity of charges. In fact, it tells us that there is a temporal variation of the, or time variation of the charge density, rho, which is related directly to a special variation represented by the divergence here, nabla, of the vector current density J. To obtain this relation, you simply actually go with the gradient or the divergence of this equation. So you will get the divergence of a curl which is equals to 0, and here you get actually the time variation of the gradient of E, which is rho, and then you get here the nabla of J, and then you get to this equation. Mathematically it's easy, but the physics behind it is interesting. Okay, so it really tells us that if there is any variation, if there is any rate of variation in time of the current density across a certain volume or surface, well, this is going to be opposite to the special variations of the current density. Okay. So if especially in the space the current density vector is going positively, then there is a negative change during time of the charge density. Okay. Now we will get back to this relation several times during this presentation. However, these representations of the Maxwell equations are not unique, which means that there is a different form which will be very useful to us specifically when we start talking about the covariant forms of Maxwell's equations, so in four vectors format. And this uses the so-called scalar potential phi, which is a function, scalar function depending on time and space, and the vector potential A. These are two entities that are related to the electric and magnetic fields through these equations. Now the thing is, and I'll put that in exercises and show you the answer for it later in a video that I will send later on, but I will give you the time to try it yourself because it's very easy. Basically, you can see that if you take these equations, these expressions of E and B, and you put them into these relations that do not contain rho and J, well, you will see that using these expressions will also yield the zeros here, which means that these expressions or these potentials, scalar and vector, phi and A, actually satisfy these two Maxwell's equations. Now you can do the exercise also by implementing the same expressions of E and B in the first two equations of Maxwell that contains J and rho, and you will find that phi and A will be related to J and rho in these forms. Yeah, it's just mathematics. But you can do it because you might be asked about it. Okay, great. Now what's important to know about these two entities, so the scalar vector, so it's the scalar potential, sorry, and the vector potential phi and A, is that These two entities are not unique, meaning that there's no specific phi and specific a. It's a fault here, I must have a vector, but that's not a big deal. These two entities are not, they could actually be obtained in different formats. And to obtain these different formats, we use something called the local George transformation. Now, what is a George transformation? So I will try to do this here, this way. Now I'm just explaining, if you want, conceptually, what would be a George. Look, if you have a chamber, closed chamber, in which you are leading gas into it and increasing the pressure in it, well, if you need to know the pressure, you need to measure it, you need to monitor it, and you use like a small graduation system. So you have graduations here. I don't know if graduations, it seems like French. I mean, you have a scale, okay? And this will tell you how much pressure you have, let's call it P, in bars. Well, this measurement system, it's called a jauge. So you are actually detecting something with a certain scale. Now, if we do something called a transformation of George transformation, well, basically it simply means that I'm actually using a different system, a different George here, which has a different scale, but it measures the same thing. Now, this George in here, it will yield to me a pressure, let's call it P prime. That's the pressure of the same gas, but it's P prime. Why? Because the scales or the grades of these two Georges are related with connected with the relation. Say P prime measures P but plus 5%. So each grade is 5% more than the grade on P. That's all. Okay? Now I'm measuring the same thing but with two different Georges. And this is the transformation, the George transformation. It's a relation between the values measured with one system compared to the values measured with another system. Okay? Well, let's go back here. Now, what it says that we can find actually expressions of phi and a, call them phi prime and a prime, that are related to phi and a through a local George transformation. For phi, it's defined by this relation, and for a, this George transformation is defined by this relation. Now, note that I have used an expression or a function called xi, or key, which is an arbitrary. Key here means nothing, it could be f4, whatever. It's a totally differentiable function over time and space. Okay? Arbitrary function. The idea is that if you take these expressions of phi prime and a prime, after you take their transformation of George here, and you implement these in the expressions of E and B, then you will be having E prime and B prime, because instead of phi you would put phi prime and instead of A you would put A prime. Now, if you replace phi prime and a prime by their values or expressions with the George transformation, you will end up to have E prime equal E, which means that whatever the choice of phi and a, whether it's phi or phi prime, whether it's a or a prime, but they have to be both in the same George, then the electric field and the magnetic field wouldn't change. And this is why we're saying that the choice of phi and a is not unique. Okay? You can do this exercise very easily. Great. One last thing before we move to the relativistic form of these equations is another condition called the Lorentz George, or the George of Lorentz. It's a condition that relates the two potentials, the scalar potential phi and the vector potential a, through this relation, which if you look at it closely, and if now I will go back to the equation of continuity, it looks like similar. Look at that. We have 1 over c time derivative of phi, which is scalar, plus the space derivative, so the gradient of A, which is a vector. A is a vector. Now, look back into the equation of continuity. It's 1 over c time variation of rho, which is a scalar, plus the space variation, so the gradient of j, which is a vector j. So they look the same, if you want. It's as if there should be a relation between rho and phi, j and a. And this relation is actually found when we use this condition in the equations of Maxwell that contains rho and j, so equation 1 and 2 on my slides. Well, you will notice that basically these two equations will decouple into two other equations that are wave equations. What does that mean? Where does the term wave equation comes from? Well, basically, if you remember, this is an operator that you probably know from quantum mechanics or from your electromagnetism course. This is a wave operator. So it's as if rho, the charge density, is actually related to phi, but it's a wave propagating of phi. And same for j. It's as if the current density is a propagating wave of this vector potential A. Okay? So it's very interesting physics going on in here. And interesting understanding. So we are choosing phi so that basically its wave propagation is nothing else than the density of charge, and we are choosing A as is its wave propagation is nothing else than the vector current density. Great. Now we have seen the Maxwell's equations in the classical forms and all the related conditions and Jones transformations, including phi and A, which represents in another way the Maxwell's equations. Now, what about the covariant forms? Because we are interested in this course basically in the quantum mechanical relativistic equations. Now, as we have seen in chapter 1, the last part of the chapter 1, I showed you that if we have a reference S in which we have a wire containing a density of charge rho, in which these charges are not moving, well, there's no current in S. However, if there is another observer in another frame, S prime, moving with respect to S with a certain velocity v, then this new observer in S prime will see a different charge density in the wire, and that's because the length contraction happens, relativistically speaking, but also this observer will detect a current flowing in the wire in his own frame S prime, and to govern or to study this Lorentz sort of transformations of charge density and current densities, we have defined the 4-vector current density J mu, which has a temporal or time component, which is the rho or C rho. In my first video I put C rho, but here I put rho. Well, the C will appear somewhere else, as you'll see, but that's basically the same. It's two different notations depending on the authors. And the spatial components are nothing else than the vector charge, current density. Now it's easy to see, if you want, that the continuity equation, which is again this one, well, if you remember from chapter 1, what is the 4 gradient or the 4-vector gradient? Well, the 4-vector gradient basically is this 1 over c time variation or variation of time plus nabla. This means that if I apply the 4 gradient or the 4-vector gradient theorem mu to j mu, which contains rho and j, well, I will get to the continuity equation that I've just seen before. But that is the covariant form, the relativistic covariant form of the continuity equation. Now, in the same fashion, we would define the four vector potential, we call it, which has the time component as the scalar vector, the scalar potential, sorry, and the space component is as the potential vector or vector potential A. Now, you can easily see again in this very similar fashion that if we apply the four gradient or the four vector gradient there on mu or there on u to the four vector a mu or a nu, well, this will yield the Lorentz condition, the Josephs-Lorentz condition, which is very similar to the equation of continuity, which is this one. Because again, 1 over c d rho over d rho t plus nabla is nothing else than the d rho mu application to a mu, which has the time component and the space component. Now, these two equations, the wave equations, if you want, that relate charge density and the current densities, well, they are obtained if we look again into this part. Look, this part is actually in a covariant form. This wave operator is nothing else than the Allenbergian, and the Allenbergian is actually, if you recall, this is the scalar product of d rho mu, d rho mu. Okay? So the Allenbergian applied to a mu, well, this component will go to 0 in the Josephs-Lorentz. Then this component will be equal to g mu, so the time part will give this first wave equation, and the spatial part, A and J, will give the second wave equation. So basically what we have done in here, in one slide, we have written all the equations that we have seen before, apart from the Maxwell equations yet, but in their covariant relativistic forms. Now, what about the Maxwell's equations in covariant forms? Well, to do that, we would have to define something called the electromagnetic tensor, or in textbooks, in English textbooks, it's called the field strength tensor. It's a tensor which is basically a matrix in here, a 4x4, that contains the components of the electric and magnetic fields. So this represents the electromagnetic field. Okay? And this defines the relation between them. It's called F mu nu. It's in the covariant or relativistic form. Okay? Well, this expression in here, it tells us that the field strength tensor or the electromagnetic tensor is actually a exterior derivative of the quadrivector potential. And honestly, I will not claim that I can do fully the mathematics behind that, or that we are responsible for it. What I can do is actually to give you a sort of an impression of conceptual understanding of this. Well, you see, F mu nu is nothing else than the electromagnetic field. So it's this electric and magnetic field that they are traveling in space-time at a constant speed, which is invariant of Lorentz, right? And the relation between these two fields that are perpendicularly moving, the one with respect to the other, as waves, they remain perpendicular even if we change the reference. So this is also an invariance of Lorentz. Now, the four vector potential A mu defines the density of charge and J, which defines the Maxwell's equations somehow, and their variation in the space-time is defined by a variation of, or by the gradient of this 4 vector with respect to x mu, because x mu contains the time component as a 4 vector position and the spatial component. So we are looking into the wave variation in time and space of a mu, which actually is related to the electric and magnetic fields, and this actually why F mu nu is the exterior derivative. Okay, so please just focus on the concept, because we are not really going into the mathematics of this, because it's well, at least beyond what we are interested in now. Now, the expressions of f mu nu and its covariant form and contravariant form is actually nothing else than a diagonal zero for the matrix. Then you have the distribution of the components of E, so Ex, Ey, Ez, or E1, E2, E3 with the minus in here in the contravariant form, and then the minus changes in here because of the change of indices, but the magnetic components remain the same. Now it's feasible, although we are not going to do it and you are not responsible for it, but the scalar product of this tensor, so the covariant contravariant scalar product, f mu nu, f mu nu, is going to be equal to 2b squared minus e squared. The idea here is this is an invariant of Lorentz because it's a scalar product. Well, this means this is a invariance of Lorentz. So in whatever reference frame, there is a relation that remains invariant between the intensity or the module of B and the module of E. Okay? And this is something that should be intuitive somehow, conceptually speaking, because these two fields, if we look into light, well, these two fields travel at a speed that is the whole basis of relativity, and it's an invariance of Lorentz, or invariant of Lorentz. Now, here I'm showing you, if you want, we are not doing the calculations, we are not going to do the calculations, but I'm showing that using the electromagnetic tensor or the field strength tensor F mu nu, it's possible to represent or to reduce the Maxwell's equations in their classic form into a set of two equations containing the field strength tensor. Well, these two equations containing rho and j are just related by the force gradient applied to F mu nu. Okay, so if you want the variation in time and space, the gradient in time space of the electromagnetic field will give us basically j nu, which is nothing else than the charge density and the current density. And if you look into the other two equations, well, they could be obtained like this. Just take it as it is, please. Accept it as it is. You are not responsible for deriving it. I'm not responsible for deriving it. We want just to see it and know it. Just for understanding it as it is, notice that it's the first derivative, or if you want, the force gradient applied to F mu rho. And here we have three indices, mu, nu, and rho. And it's like a determinant or a Jacobi identity. So notice that the alternation or the way the indices change. So it's mu, rho, nu, and then nu comes here, rho comes here, and nu comes here. So we have d rho nu f rho mu, and then rho comes to here as an indices. So d rho f mu nu equals to 0. Well, in fact, in absence of charge, so if we have here no charge density, which means that this is going to have a temporal component of 0, and j will equal 0, so this is going to be equal 0. It's possible to demonstrate this one using, if you want, the metric, the Lorentz metric, by lowering the indices, but we are not going to do it. You are not responsible for it. Great. Now that we have the Maxwell's equations in their covariant forms, and we have a lot of things that we have seen so far in terms of equations in their covariant form, let's see an application, simple one, if you want, of a charge, so a quantum system, an electron, let's say, that is in motion in an electromagnetic field. Now, before I go into explaining this expression of Lagrangian, let me talk to you about what we probably, or you probably, have seen in electromagnetism about a charge moving at a speed v inside an electric and magnetic field. Well, there is a Lorentz force that applies to this electron, or to this charge, which is Q v plus, E plus v scalar v curl B. This is the Lorentz force, right? Now, there is a force on a charge moving, then we could actually get the equation of motion of it using the second law of the fundamental law of dynamics, or the second law of Newton. So dp over dt, or we can actually, as we said, I'm talking classically so far, or we can actually use the Lagrangian formalism, and the equation of motion comes from the Euler-Lagrange equations. Now, if you apply the Euler-Lagrange equations, you are not responsible for it, but if you are interested, I can give you the link to it. So if we get the Euler-Lagrange equations and we compare them to the dp over dt that we could get knowing the force equal q E plus v curl b, then we could actually find the expression of the Lagrangian that satisfies this for the charge inside the electric and magnetic fields, which is given classically by q minus phi plus v scalar a, where phi and a are nothing else than the scalar potential and vector potential that define E and B in a different way. Well, it's in a similar fashion that actually we get the Lagrangian of this charge in the covariant form. So as you have seen before, we had for a free charge or for a free particle with no potential, we had minus mc squared over gamma, because the square root of u mu is nothing else than c. That was the expression, the covariant expression of the Lagrangian. If you review your chapter, sorry, if you review the chapter before, the video before. Well, now we have to add this part to it, because we actually have the electromagnetic field now applying. So there is the part on v scalar a, if you want. Then, well, the c here that appears, so first, the gamma is nothing else than gamma L, because gamma L is invariant of Lorentz. So we add gamma here. Now c is basically because, as I said earlier, in this f nu, I have written E1, E2, E3 minuses also. In a lot of textbooks, people divide here by C, right? And if you divide here by C, then the C in here does not show up. Anyway, so the interesting part is that that's the form of the Lagrangian, covariant Lagrangian for a charge in an electromagnetic field. Now, if you actually do the Euler-Lagrange equations in their covariant forms, so that's derivation with respect to x mu and then with respect to u mu of gamma L. So you take this gamma L that you can take from this expression, you do the Euler-Lagrange equations, you will realize that this relation shows up, which is dp mu over d tau equals to over c f mu nu u mu. And this is obviously the force. So what this relation tells us that the four-vector force on the charge moving in an electromagnetic field is E over c, which is the charge itself, times the electromagnetic tensor and the speed, or the quadrivector or the four-vector speed of this particle in this electromagnetic field. This is also something that I will give you the possibility to derive it yourself, and then later on I will send its derivation and explained in a video on the exercises. Well, this ends our video now, and we still have two types of relativistic equations that we need to deal with later on.